Hello, this is Mechan 2040 Solid Mechanics. I am Globus from Year 3 of Aerospace Engineering. So today we are going to discuss about one of the most important topic, which is about torsion. Firstly, we will try to derive the elastic torsion formula by discussing different properties of a prismatic bar. Besides, we will talk some examples of statically indeterminate problems. Apart from that, the stresses on inclined planes caused by pure torsion will be discussed. The torsion of thin-walled shafts will also be simply introduced. First, let's discuss about the elastic torsion. Consider you have a cylindrical shaft with the fixed end being twisted by a torque acting on the tip. The external torque then will be transmitted along the length of the bar. Then for every cross-section inside the bar, there will be torsion inside it, like this. We want to derive a torsional formula of the simplest form. So we first consider a prismatic bar with uniform cross-section and constant material properties, which is the shear modulus. A torque acting on tip of the bar causes torsional displacement phi x at every location x on this prismatic bar. First, let's consider this prismatic bar. We fix one of the ends. When a torque is applied on a free end of a circular bar, something like this, the angle of rotation will vary nearly linearly. That means the function phi x will be a linear function with respect to x. The angle of rotation will vary linearly from 0 at this fixed end, because we know at the fixed end there is no torsional displacement because it is fixed. But for the free end, it is possible to be twisted, it is possible to rotate for some extent of angles. At the fixed end, we say the displacement is phi. Then the torsional displacement has a unit of radian. We don't say what is the size of this angle in degree when we are doing the calculation. But after we found the angle of phi in the unit of radian, we will convert the answers to degrees when solving the problems. Next, let's talk about the notation of torque. Actually, there are two kinds of notations available for torque. One is the double arrow form, and the one is the direction of the twist. Basically, as you can observe, those two kinds of notations are related by the right hand rule. That means when you are using your right hand, then your thumb is pointing to the direction of the double arrow, while the rest of your four fingers are twisted like this. It is similar for the torque to the left hand side. There is an advantage to express the torque in this way in the double arrow form. That is, you can easily identify that, okay, this is a positive torque. Why? Because in our previous axial load cases, this is called tensile load, which is positive. And as you can see, when we are talking about the torque, we also have two double arrows pointing outward. Then we can say it is a positive torque. So positive torque means this piece of material is twisted like this. And similarly, if a piece of material is under a torque like this, in the axial load case, we know that it is compressive, it is negative, but in the torsion case, we say it is a negative torque. Then what is the negative torque? By using your right hand rule, it is easy to identify that the bar is twisted like this. So here we also discussed the sign convention of the torque. Next, we talk about the rate of change of angle of twist. We discussed previously that the angle of twist changes with respect to x almost linearly. Since it is linear, that means d phi dx equals to a constant. So we have to define what the constant is. We can define a constant, say theta, to express the derivative of phi x with respect to x. We call it the rate of change of phi x with respect to x. Then we have the constant theta equals to d phi dx equals to the angle of twist at the end of the bar divided by L. Next, we have to discuss in detail about the shear strain on the surface of the shaft. Consider a small angle of twist phi at the free end here. Notice that in this diagram, the size of phi is highly extravagant. In the reality, the size of phi is often very small. When this angle is small, the angle QPQ prime is very small, and the line PQ prime, which is this line, is almost a straight line. Then we consider this free end. At this free end, since the angle of phi is very small, the arc length QQ prime is almost a straight line, and the length is R phi. So consider this very small sector for this very small angle phi. Then you cut it in half. For this sector, since the phi is very small, the line QQ prime is almost a straight line. Then we can treat it as two right triangles. For each of them, it has an angle of phi divided by 2. Then the length of the small segment will be R times phi divided by 2. Then the length of QQ prime is given by R times phi over 2 times 2 equals to R phi. For everywhere on the surface, the shear strain of elements are the same. Or in another word, it is assumed to be the same. As what we have learned in previous tutorials, the shear strain of a material is just the angle QPQ prime. But for this very tiny angle, by using the small angle approximation, it is just tangent of angle QPQ prime. Then it equals to the length of this arc, which is R phi, divided by the length of the bar, which is R phi divided by L. But we know that phi over L is just the rate of change of angle of twist, so it is simply R theta. Notice that the shear strain on the surface is the maximum. So in case you are talking about the shear strain inside the material, then for any element located inside the material, its distance from the center of the circular prismatic bar must be less than the radius of it. Consequently, the shear strain inside the bar must be smaller than those elements on the surface. Therefore, we conclude that shear strain on the surfaces is the maximum. Now we talk about the shear strain inside the shaft. For an element located at distance ρ on an untwisted cylindrical surface inside the shaft, similar to those elements on the surfaces, the elements inside the bar will also be twisted. Then all what we need to do is replace the R by using the ρ. Maximum shear strain is on the surface, which is R phi divided by L. So here we just replace the R by using the ρ. From our previous discussion, it is not that difficult to observe that the shear strain of elements inside the bar is directly proportional to the distance ρ from the central axis, where the proportional constant is theta equals to phi divided by L. As we have already discussed in the previous slide, we just rewrite this formula a little bit. Then you can see we take out phi divided by L equals to theta out. Since those two stuff are constant, then gamma equals to a constant times ρ, where ρ is a variable. After talking about the shear strain inside the bar, we talk about the shear stress. Recall the shear stress formula, tau equals to G gamma, and we have already got gamma equals to this. Then we just times G to the shear strain to get the shear stress. As what we just discussed, phi divided by L is a constant, theta equals to phi divided by L is also a constant, G is supposed to be a constant as well, so those two parts will become constants. Then the shear stress equals to constants times the ρ, which is distance from the center. This formula shows that the shear stress is linearly distributed inside the bar. Notice that this phenomenon is also valid for hollow shafts, and it will be left to you as an exercise to prove it. For the maximum shear stress, we just use the maximum shear strain times the shear modulus. The result will be like this. Consequently, we can find the ratio of shear stress of any element inside the bar to that of the maximum. We found that this ratio equals to ρ divided by R. Then we can write the shear stress inside the bar to be tau equals to ρ divided by R times tau max, where ρ divided by R is a kind of ratio. This is a figure drawn from our previous lecture notes, talking about the shear stress of every element inside the prismatic bar. when a torque is applied on this end, for those surfaces, when there's a torque acting on the end of the bar, those surfaces are directly affected and there will be shear stress acting on it by the torque directly. For the rest of shear stresses on element, they are all caused by the applied shear stress by the torque. They are called the complementary shear stress. And somehow, there is an important conclusion that we can draw from the applied shear stress and the complementary shear stress. Consider a little piece of differential element. For this coordinate system, this shear stress is acting on positive x surface pointing to the negative y direction. Therefore, it is called negative tau xy. For this tau xy, there will be complementary shear stresses acting on the rest of the three surfaces. Take the moment above P and consider the moment equilibrium. First, for shear stress on each surface, we consider the shear force acting on that surface. The force acting on this surface is tau yx dx dz. So this is the force minus tau yx dx dz. It has a distance dy from P. Similarly, for tau xy, we can also take the moment. In this case, it is in the opposite direction because tau yx dx dz dy is talking about twisting P to this direction, while for minus tau xy dy dz dx, it is talking about you have a force minus tau xy dy dz times this dx, and it is tending to twist this element in this direction. So this is why there is a negative sign in between. By simplifying the above expression, you know we have dx dy dz, then what we left is just tau xy equals to tau yx equals to a magnitude of the shear stress. The result will be the same no matter where you take the moment. After discussing tons of properties of the circular bar, now let's derive the elastic torsion formula for a circular bar. Consider the cross-section. For each element in the cross-section, there is shear stress, tau. For an arbitrary element on the surface, it has a distance rho from the center line of the cylindrical prismatic bar. Since for the entire chapter we are talking about there is a torque acting on the cross-section, therefore we also need to find the differential form of the torque such that we can sum up the torque for every differential area element on this surface. The differential torque of an element on the cross-section dt equals to the shear stress tau times the differential area. So those two terms multiplied together generates the force, which is dF. Then we times the differential force by the distance rho from the centroid to get the differential torque, which is given by tau rho dA. Next, we substitute the relationship between the shear stress and the maximum shear stress into it. The differential torque can be rewritten in this form. Then we do the integration on both sides, and we also take this constant out, such that we get this result. Now we define a quantity called the polar moment of inertia, which is given by the integral of rho squared dA over the entire region. Then the torque can be written as T equals to tau max J divided by R. However, although we get this result, who knows what is tau max, right? We don't know anything about it. We cannot observe it directly from the shaft. Therefore, our ultimate target is to express the torsional deformation in terms of applied torque. Consider the tau max, since we know that, so the maximum shear stress inside the shaft is given by G times phi divided by L times R. Therefore, we substitute this stuff into the tau max, then we get this. At the same time, we can cancel the R out, such that eventually we get T equals to G phi J divided by L. Finally, we rearrange the terms such that we make the phi to be the subject of this equation. Then we get the elastic torsion formula, which is phi equals to TL divided by GJ. Notice that it is rather comparable to what we have learned before, which is the axial deformation of a piece of material under the axial load. Delta equals to PL divided by EA. So in such case, P and T are loads acting on the prismatic bar. L are the length of the material. G and E are material properties. J and A are sectional properties. So as you can observe, they are rather similar and comparable. It is an extremely important result that you will frequently use in a lot of applications about the pure torsion. It will be illustrated in the examples. Finally, let's talk a little bit about polar moment of inertia. The polar moment of inertia is defined as, for the entire region A, we have the integral of rho squared times dA. Notice that for this integral, the distance from the center rho is already defined in the polar coordinates. That is, we have the rho axis and also we have the theta. Well, you can ignore this notation if you think it is too complicated, but the basic idea is that adopt the differential area element in the polar coordinate system. As what we have discussed in tutorial 0, to do this integral, we can do this. J equals to the integral of rho squared dA. But you know, for the polar coordinate system, differential area dA is just rho d theta. Then we can compute the polar moment of inertia of a circular cross-section. J equals to rho squared dA equals to rho squared rho d theta. So this one is just simply dA. And also we consider the lower and upper limits of rho and theta. For rho, its range is from 0 to r, while for theta, it is from 0 degrees to 2 pi. Therefore, we have the lower and upper limits of rho is 0 and r respectively. That of theta is from 0 to 2 pi. Then we have 2 pi times the integral. We have the integral of rho cubed d rho from 0 to r. So the polar moment of inertia is given by pi d to the power 4 divided by 32, where d is the diameter of the circle. Or you can express it simply in the radius, which is pi r to the power 4 divided by 2. Similarly, for the hollow circular tube, the computation of polar moment of inertia is rather similar, with one thing you have to modify, that is the lower and upper limits of rho. In this case, rho is from r1 to r2, so the lower and the upper limits will become r1 and r2 respectively. Similarly, you get this integral, and you evaluate this integral from r1 to r2, which gives you this result. And you can convert this result in terms of diameter, such that you have pi divided by 32 d2 to the power 4 minus d1 to the power 4. For multiple shaft and the continuously varying shaft, I just give you some very simple introduction about those formula, and you will mainly concentrate on the application of them. For shafts with multiple cross-section, you just sum up the torsional displacement for each segment. For shafts with continuously varying section, you just do the integration. Let's do a closing review, a very quick review of what we have learned in this section. Torsion will generate a torsional displacement phi at the free end. At the beginning, we define the rate of change of torsional displacement, theta equals to phi divided by L. Besides, we also introduced the shear strain formula, which is given by theta times rho. The torsional displacement at the free end will cause the shear strain inside the bar, which is given by gamma equals to theta rho equals to rho phi divided by L. Notice that the maximum shear strain occurs at the surface of the shaft. So in such case, you just put rho by r. In previous tutorials, we discussed the relationship between the shear stress and the shear strain. Therefore, we apply tau equals to g gamma to those shear strain formula. Notice that all those stuff above are just the foundation for us to derive the elastic torsion formula. After reviewing those foundations, we talk about what we really did to derive this formula. we considered a differential torque dt equals to tau rho dA, and we substitute the shear stress relative to the maximum shear stress. Then we can rewrite this differential form in this way. Then we do the integration on both sides of the differential form to get this, where we define the polar moment of inertia to be J equals to the integral of rho squared dA. Then the torque acting on the free end of a piece of material can be expressed in this way. Finally, we substitute the maximum shear stress into this equation such that we can get the torque expressed in terms of shear modulus, torsional displacement, polar moment of inertia, and the length of material. Finally, we make phi to be the subject, the elastic torsional displacement. Then we get the elastic torsional formula, which is phi equals to TL divided by Gj. Notice that it is very similar to what we have learned in previous chapter. Delta equals to PL divided by EA. Then we can find the torsional displacement based on the loading conditions. We also derived some important conclusions of the polar moment of inertia. For solid circular shaft, the polar moment of inertia is pi r to the power 4 divided by 2 equals to pi d to the power 4 divided by 32. For circular tube or the hollow circular shaft, the polar moment of inertia is given by J equals to 1/2 of pi times R2, the outer radius, to the power 4, minus the R1, the inner radius, to the power 4. And it also equals to pi divided by 32 times outer diameter D2 to the power 4, minus the inner diameter to the power 4. After talking tons of theory and the formula about the elastic torsion, let's try to apply what we have learned to a practical problem. The elastic motor exerts a 500 Nm torque on the aluminum shaft ABCD when it is rotating at a constant speed. Knowing that the shear modulus G equals to 27 GPa and the torque acting on B is 200 Nm and the torque acting on C is 300 Nm. We want to determine the angle of twist between B and C and C and D. Also, we want to determine the maximum shear stress inside the entire shaft. For the first problem, we sketch this circular shaft by this simplified schema by using the right-hand rule, because previously we mentioned that by using the right-hand rule, you can clearly know that whether the torque is positive or negative. Firstly, we draw those two known torques on this shaft. We draw it from A to D, like this. Then at point B, there is a torque rotating in this way, and you are the observer standing here. Then, by using your right-hand rule, the thumb is pointing to the left-hand side. Therefore, you can write this torque in this form. Similarly, for the 300 Nm torque, as an observer, you are standing here and you are observing this torque. By using your right-hand rule, you can see that the torque can be sketched in this direction. Your thumb is still pointing to the left-hand side. Therefore, you can draw the 300 Nm torque in this way. At the same time, we notice that there is no torque at point A. Besides, the whole system is rotating at a constant speed. That means there is no total net torque on this system. Consequently, there must be a reaction torque, which is 500 Nm acted by the motor on this circular shaft. Notice that although the motor is rotating very fast at this end, but we treat it as a fixed end. You may wonder why the end D is treated to be a fixed end. Although the engine is always spinning at a very high speed, but the problem is that there must be some component that fixes the shaft at point D such that it can drive the shaft to rotate. Now we are interested to the angle of twist between B and C and B and D. To do this, first we consider each of the segments required. For segment BC, by using the double arrow notation, we can immediately know that there is a 200 Nm torque, which is positive, acting on this piece of material. Then you can find the torsional displacement directly by using the formula. One reminder is that the diameter of the circular shaft is not uniform. For AB, it is 40 mm, for BC, it is 44 mm, and for CD, it is 48 mm. So be careful with it, because when I do this problem for the first time, I forgot to observe the difference of the diameter, then I got the wrong answer as well. So be careful with it. The torsional displacement of B relative to C can be found by using this formula. Torsional displacement of B relative to C equals to the torque acting on the member BC times the length of BC divided by the shear modulus, and you divide by the polar moment of inertia of the segment BC. The torque is 200 Nm. The length of member BC is 1.2 meters. The shear modulus is given by 27 gigapascals. The polar moment of inertia is given by pi d to the power 4 divided by 32. After a lot of simplifications, you can find the torsional displacement is 1.384 degrees. Similarly, for section BD, you have to observe the torsional displacement in segment CD as well. Consider the torque on CD, since this end is already under a torsion of 500 Nm. Then for this end, it must be 500 as well. So the torsional displacement on segment CD is given by the torque acting on this segment times the length of member CD divided by the shear modulus divided by the polar moment of inertia of the segment CD. The torque acting on it is 500 Nm. The length of CD is 0.9 meters. The shear modulus is 27 gigapascal, while the diameter of segment CD is 48 mm. Therefore, you can find the torsional displacement of C relative to D, which is 1.832 degrees. Therefore, we sum up the torsional displacement of C with respect to D and the torsional displacement of B relative to C. Then, adding the result in part 1 and the part 2, you can find the torsional displacement of B relative to D, which is 3.216 degrees. Part B requires us to find the maximum shear stress inside the aluminum shaft. Notice that although the elastic torsion formula phi equals to TL divided by GJ is given in the formula sheet, sometimes it might ask you some embarrassing problems such as this: maximum shear stress. You might forget it, right? So for the maximum shear stress, it is given by G times the maximum shear strain. Then you rewrite this formula in this way, so still you have to remember those things. But in this problem, there is no radius given, it is just the diameter, so we just put R to be d over 2. Then we rewrite this maximum shear stress into this form, which is Td divided by 2J. Then we're interested to find the shear stress in each segment. For segment AB, there is no shear strain because A is a free end and there is no reaction torque acting on it. For segment BC, it is subject to a 200 Nm torque. Therefore, the maximum shear stress in segment BC is given by Td divided by 2J of BC. Then you do kinds of simplifications. Finally, you get the maximum shear stress is 11.96 MPa. For segment CD, similar manner, we substitute the stuff into it to get the maximum shear stress in segment CD is 23.03 MPa. Compare all those results, we found that the maximum shear stress in the shaft is just the maximum shear stress in segment CD, which is 23.03 MPa. After discussing a problem about multiple shafts, now let's discuss a continuously varying bar. A torque T is applied as shown to a solid tapered shaft AB. We cannot use phi equals to TL GJ anymore. No, we cannot use it. Show that by integration that the angle of twist at point A is phi equals to 7TL divided by 12 pi g times c to the power 4. C is the radius of the upper surface, while 2c is the radius of the lower surface. In this case, still we assume g and t are constants for the entire bar. However, J is a varying quantity with respect to x, because J equals to pi divided by 2 r to the power 4. But in this case, r is not a constant. R is varying with respect to x in this case. So in this case, we know that the torque is the same to all the cross sections inside the shaft, and the shear modulus is assumed to be the constant. However, J is a variable of x because you know J equals to pi divided by 2 times 2r to the power 4. But in this case, r is a variable instead of a constant. Therefore, we must obtain an equation of r in terms of x. So we know that at x equals to 0, the radius is 2c. X equals to 0. When x equals to 0, the radius is 2c. When x equals to L, the radius is c. Then we can write the linear equation like this. By a series of simplification, we get Rx equals to minus c over Lx plus 2c. Then we can rewrite Jx in this form. We can rewrite the polar moment of inertia in this form, but since it is power 4, which is an even number, then we can just switch the symbol inside this bracket. So the polar moment of inertia will be written in this form. Before we integrate this stuff, consider this integral and the Jx. Later on, the Jx will be put in this integral and it will be integrated. To simplify this integration, let u equals to c divided by Lx minus 2c, then dx equals to L divided by c times du. The lower and the upper limits of the integral consequently will become minus 2c to minus c respectively. Now we consider the torsional displacement formula in the integral form, which is this. Now we put our Jx into it and we take this constant out to get something like this. Also, since dx equals to L divided by c du, so there is an L divided by c occurred here, then the whole bracket becomes u, and the integral becomes du divided by u to the power 4 from minus 2c to minus c. Consequently, keep doing this integration, you will find the final answer to be verified like this, exactly the same. So it is left you to read. Well, for statically indeterminate torsional problems, there are not much stuff to talk with. When dealing such kind of problems, we often deal with the continuity of torsional displacement and the boundary conditions such as the fixed end, the clamped end, such that we can get additional equations to solve for the unknowns in this system. Now let's talk about a statically indeterminate problem. It is designed myself and hope you enjoy it. Two solid cylindrical bars AC and CD of equal length L are welded at C. That is, for AC, its length is L. For CD, its length is also L. The whole piece AD is clamped to the fixed ends at A and D, so those two ends are fixed. Bar AC is drilled such that the segment AB is a hollow circular tube. So in this part, it is a hollow circular tube, and it is connected to a solid cylindrical shaft. We now define some dimensionless quantities. Let D2 equals to PD3 equals to PD, where P is greater than 1. That means the diameter of sections 1 and 2, I mean the blue bar, is greater than that of the segment CD, which is the brown bar. So for the brown bar, we can write it this way. We can draw a table over there. So talking about the diameter of the brown bar is D, while the diameter of the blue bar is PD, where P is greater than 1, means that the diameter of the blue bar, or the outer diameter of the hollow circular bar, is greater than that of CD. Besides, the shear modulus of segment CD is G, while the shear modulus of AC is QG, where Q is less than 1. That means the strength of the blue bar is lower than that of the brown bar. Besides, we also define the ratio between the drilled length of the blue bar to that of the entire length. So consider this blue bar. It is drilled in the middle. We call the length of the drilled segment to be L1, and we know that L3 equals to L1 equals to L. That is, the length of the entire blue bar is L. So S equals to L1 divided by L less than 1. So those dimensionless quantities will be used in part B of this problem. First, let's consider an easy problem in part A. A torque of 500 Nm is acting at point C. Here we just mark it in this double arrow pointing to the left hand side. F L1 equals to L2 equals to 1/2 of L equals to 300 mm. That means the length of the drilled part equals to that of the undrilled part. L1 and L2 are equal. Besides, G1 equals to G2 equals to 35.04 gigapascals. So it is the material property of G1 and G2. G3 equals to 157.95 gigapascals. The material property of the brown bar is much more stronger than that of G1 and G2. Given that the diameter of the blue bar is 30 mm, that is also the outer diameter of the hollow circular segment. D3, which is the diameter of the stronger brown bar, is given by 20 mm. Besides, you are also asked to verify that in case the reactions at fixed ends A and D are the same, then we have the relationship P to the power 4 plus S minus 1 divided by QP to the power 4 times P to the power 4 minus 1 equals to 1. Consequently, I will ask you to verify that your answers in part A is reasonable. I can give you a little hint here. The reaction at A and D in part A should be the same because all the given conditions here satisfies this equation. So it is a very important hint to you. In case you cannot get the same answer of the reactions at A and D, you can still get some marks from B and C. Besides, there is a difficult problem for you to think of. If a torque is acting at point C still, find the threshold value of P such that it is impossible that the reactions at A and D are the same. That is, under the allowable range of the ratio between the material strength, how large the diameter of the blue shaft should be such that the reactions at A and D are impossible the same. To do part A, first we consider the statics. By using the statics concepts, we know that TA plus TD equals to T. Bear in mind how to read this diagram. For this diagram, you still can imagine that you are using your right hand to rotate, to twist this tube in the middle, then your thumb is pointing to the left hand side. Consequently, on the fixed ends A and D, there will be a resisting torque, TA and TD, which is trying to rotate this rod back to its original torsional displacement. That is, when you try to twist this bar back, then for TA and TD, by using your right hand, the thumb is pointing to the right hand side. Apart from that, so this is all what we can know from statics. Next, we have to obtain additional equations to solve this statically indeterminate problem, because obviously we can draw no conclusion from this statics result. However, one thing you can bear in mind is that the torsional displacement of C relative to A plus the torsional displacement of D relative to C should be 0. That is, from A to C, the torsional displacement is like this. Then this is just phi of C relative to A. Then from C to D, the torsional displacement will be going like this. So this is called phi of D relative to C. Since both ends are fixed, that means the torsional displacement at those two ends are 0. Now we have the compatibility equation obtained from the torsional displacement. Now we find the polar moment of inertia of each of the cross-sections. The polar moment of inertia of segment 1, which is the hollow circular segment, is given by this equation. Then you substitute the values. The outer diameter of AB is 30 mm, while the inner diameter is 20 mm as mentioned in the problem, because the diameter of the inner part is the same to that of the bronze shaft. For J2 and J3, similarly, you can obtain the sectional properties in this way. Next, we compute the torsional displacement of each segment one by one. For segment BA, the torsional displacement at B relative to A equals to minus TA L1 divided by G1 J1, because for AB, this hollow shaft, it looks like there is a TA here and then apply torque T here. Since both of them are pointing into the material, that means the torsional displacement caused by the torque is negative, and consequently this torque is a negative torque. Therefore, we have the negative sign located here. By substituting all the possible values into it, and what we left is just the TA. The torsional displacement at point B relative to A equals to minus 2 divided by 4745 pi times TA divided by meter. Similar for phi C relative to B, the torsional displacement at point C relative to B equals to minus TA times L2 divided by G2 J2, but you know G1 equals to G2, so those are the same. Substituting all those values inside, then we have this complicated result. Finally, we sum both of them up to get this result. The torsional displacement at C relative to A equals to minus 4TA divided by 5265 pi Newton meter. Next, we consider the torsional displacement from C to D. We substitute the shear modulus of D as well as the polar moment of inertia into it. Then we will get this. The torsional displacement of D relative to C equals to 40D divided by 5265 pi Newton meter. By using the compatibility equation, we can get this result. That is, we substitute our torsional displacement of D relative to C as well as the torsional displacement of point C relative to A into this compatibility equation. Then this compatibility equation is converted to equation of TA and TD, which are two unknowns that we are going to find. Obviously, from this equation, you can see it gives you the result of TA equals to TD. Since TA plus TD equals to 500 Newton meters, as mentioned in the statics part, then we can find the torque at point A and D. At both point A and point D, the fixed wall gives a positive torque of 250 Newton meter to this shaft. At both A and D, the fixed wall gives the torque of 250 Newton meters. Consequently, the torsional displacement at point C is given by this. Then you just substitute our TA into this equation to get our torsional displacement, which is negative 3.464 degrees. Next, let's talk about this very algebraic problem. It involves a lot of dimensionless quantities. It is given that the reactions at fixed ends A and D are the same, which means TA equals to TD equals to 1/2 of the applied torque, which is T divided by 2. Consider the polar moment of inertia of both cross-sections and try to express it in terms of those dimensionless quantities. D2 equals to PD3 equals to PD. Then we just substitute it into it to get p to the power 4 times d to the power 4. Well, d3 is simply d, then it is just d to the power 4. Then you will have this content in this bracket. Similarly, the polar moment of inertia of cross-sections 2 and 3 can be found in this way. Now we evaluate the torsional displacement on the segment AC. Similar to what we did previously, we first find the relative displacement of B relative to A, then find the torsional displacement of C relative to B. You substitute the torque into it, as well as the length modulus and the cross-sectional properties. Then you find the torsional displacement of B relative to A equals to this. Similarly, for the torsional displacement of C relative to B, first you place your torque into it, but notice that what is L2? We know that L1 equals to SL, then L2 equals to L minus L1, which is 1 minus S times L. We also place this polar moment of inertia into this expression, then we get this result. Consequently, by a lot of calculations, you will find the torsional displacement of C relative to A, which looks like this. By very similar manners, we compute the torsional displacement from C to D. Finally, we substitute both the results into the compatibility equation. Then we can have such kind of expression. By simplifying it, we can have the result that we are going to prove. In part C, we are going to verify that our answers in part A is reasonable. It is shown in part A that the reactions at A and D are the same. Now we are going to use the result in part B to verify that it is reasonable. First, check the ratio between D2 and D3, which is the ratio between the blue bar and the brown bar. The ratio equals to 30 mm divided by 20 mm, which equals to 1.5. Next, by considering the ratio between the shear modulus, G1 divided by G3 equals to 1168 divided by 5265. Consider the blue bar. The ratio between the drilled length to that of the entire length equals to 1/2. Then we compute the numerator and the denominator, and we get the same result, which is 4.5625. By the numerator dividing the denominator, we have the value is 1. That is, our equation in part B is completely verified. All the given conditions in part A satisfies the equation in part B. The final answer shows that the reactions at A and D are the same. Consequently, our answers in part A is reasonable. But in this problem, we have a very critical limit. If the diameter of the blue bar is too big, to some extent, the reactions at A and D would no longer possible to be the same. Therefore, we cannot make the diameter of the blue bar too big. Otherwise, it is impossible to make our problem in part A occur. If a torque still acting on point C, find the threshold value of P, the ratio of diameter between the blue bar and brown bar, such that it is impossible that the reactions at A and D are the same. That means we want to make the diameter very, very large, such that this equation is no longer valid. We want to void this equation. By observing this equation carefully, we observe that when P tends to infinity, when P is large, this equation will tend to 0. The result shows that when the denominator is large enough, then we can make the equation void. In another word, if P is large enough, No matter how we adjust the value of Q and S in the allowable range, recall that our allowable range is this. No matter how we adjust Q and S, the equation will become void. Consequently, in order to fight against P, we want to drag the denominator down and pull the numerator up. That is, since we are going to find the threshold value, we will try our best in the allowable range to make this equation valid first, such that when we have already chosen the optimal values of Q and S, we can say, okay, the P we reached will be the threshold value such that it is impossible to make this equation valid. To pull the numerator up and drag the denominator down, let's set Q equals to the minimum value, which is 0.15, and S equals to 1. We expand this equation in this way, such that both sides are polynomials. Then we rewrite this equation in this way. Notice that we can write P to the power 4 as a quadratic term. Put our optimal value of Q and S into this equation, then we can have this inequality. Consider this quadratic inequality with the unknown P to the power 4. Simplify this inequality and solve it, then we can have P to the power 4 is less than 0, or P to the power 4 is greater than 23/3. Consequently, when the value of P to the power 4 is greater than this value, then the equation will become void. Therefore, the threshold value we are going to find is 23 divided by 3 to the power 1/4. The result is 1.664. Notice that the threshold value of P is largely constrained by the ratio between the shear modulus of the blue bar and the brown bar. After discussing the statically indeterminate problem, let's move on the stresses on inclined planes. Similar to the axial load, in the pure torsion case, we also have stresses on the inclined planes. Now, a bar is under a torque like this. For the square element inside the bar, it will have the shear stress sketched in this way. Since we know that the shear stress tau xy equals to tau yx in the previous tutorial, then we can sketch the stress element in this way. Therefore, we can derive the direct stress and the shear stress acting on this inclined plane by using this triangular wedge. Next, we decomposite tau xy and the tau yx in the direction of x alpha and y alpha. Now we do the static equilibrium of this triangular wedge stress element. Consider the area of the inclined plane to be dA. Then the area of this surface will become dA cosine theta, while the area of the surface at the bottom is dA sine theta. Since the stress on both of the surfaces are the same, which are tau xy, then we just simply write it to be tau. By checking the static equilibrium, we decompose those two forces into the x alpha and y alpha directions to get those two equations. Consequently, we will have this. By simplifying the equations shown above, we can have the direct and the shear stresses on the inclined planes. The direct stress in the alpha degree inclined surface is given by tau sine 2 alpha, while the shear stress of an alpha degree inclined plane is given by tau cosine 2 alpha. Now let's talk a little bit about the angle of inclination alpha and some special cases of stress elements of pure torsion. For every inclined element, there are two alpha surfaces, namely here and here, as well as two alpha minus 90 degree surfaces, namely those two. How do you obtain the value of alpha? Consider originally you have an element like this, it is not inclined. Next, you rotate it by an angle of alpha, counterclockwise. Then the element will be like this. This element is rotated counterclockwise by an angle of alpha. So this is how we can obtain the alpha. Then consequently, those two surfaces can be treated as alpha minus 90 degrees. The first special case we would like to discuss is the 45 degree oriented element. For this element, there are two 45 degree surfaces as well as two minus 45 degree surfaces. For those two values of alpha, for the red curve, it is representing the direct stress on the element. On the 45 degree surface, there will be maximum direct stress occurred on those two surfaces with the magnitude of the shear stress on that surface. For the negative 45 degree surfaces, you have the minimum of the direct stress, which means that for those two surfaces, there will be a compressive axial load acting on those two surfaces with the magnitude of the shear stress on that surface, but it carries negative sign. Besides, we observe that for both of the two angles, consider the purple curve representing the shear stress. There is no shear stress on those two alpha values. That means for the entire stress element, there is no shear stress acting on it. Another special case is the non-oriented element. Observe this curve, you can see that there is no direct stress acting on each surface. Besides, for this element, we only have the pure shear. At alpha equals to 0, the shear stress is the positive tau. Then we can draw this arrow first, which is tau. Then consequently, still remember our Valentine's Day joke? That is, they should have another arrow which is kissing this arrow. Similarly, you can draw the rest of the two arrows like this. So on this element, there will be shear stresses like this. The case I am going to describe here is actually not a kind of special case, but personally I think it is more special than general case, which is the 22.5 degrees oriented element. For this element, as you can see, at the 25.5 degree surface, the direct stress and the shear stress curve intersects here. Similarly, for the minus 67.5 degree surface, those two curves intersect here. We can draw the conclusion that the magnitude of the direct and the shear stress shown here are all the same. This is why I say it is relatively more special than other general cases. The magnitude is actually tau divided by square root 2. And similarly, for the 22.5 degree clockwise oriented element, you can observe that the magnitude of the direct stress and the shear stress are the same. Now let's discuss the stress elements under the general case. So just now we discussed 4 special cases for the stress elements under the negative torque. Now let's discuss about the general case. Under any pure torsion case, what will be the direction of stresses on a stress element in a bar? For general case, when we find there is a stress element inclined like this, observe that when there is a negative torque, there is a shear stress which is pointing upward on the right hand side of the stress element. Then this shear stress will be transmitted through this bar until it touches this inclined surface, and eventually, since this surface is better aligned with this vertical shear stress, then we can conclude that there is a shear stress pointing upward along this inclined surface here. But still remember our Valentine's Day joke? Once you know one of the shear stresses acting on a stress element, you can draw the rest of them easily. Then all the shear stresses on this stress element is done and finished. What we need to do is just to find the magnitude of shear stress on this element. Next, about the direct stress acting on a stress element, you can observe from our general cases below that when the torque is negative, the direct stress on the stress element is tensile in this direction, kind like in this direction. So no matter how a stress element is oriented, in case the torque acting on the bar is negative, then we can say that the direct stress is tensile in this direction and compressive in this direction. As you can observe in the previous special cases, for all stress elements except the 0 degree case, for the rest of the cases, there was always a pair of tensile stress and a pair of compressive stress acting on a stress element. So in general, for a stress element, there are 8 forces acting on it, 4 shear stresses, a pair of tensile stress, and a pair of compressive stress. Those stresses combined together will give 8 stresses acting on the stress element. And similarly, for the positive torque, you observe that on the right hand side there is a negative torque. There is a negative shear stress transmitted through the length until it touches this face, which is much better aligned to this vertical shear stress. Therefore, for this dominating surface, we call it dominating surface. We can draw the shear stress in this direction, following the direction of this shear stress. So a dominating surface is the surface that is better aligned. For the positive torque, the case is rather similar. This surface is better aligned to this vertically downward shear stress. Therefore, we can also draw a downward shear stress on this surface. Actually, I named this surface to be the dominating surface. So the definition of dominating surface is that this surface will absorb most of the shear stress transmitted from right hand side. When this shear stress is transmitted to this inclined surface, since it is better aligned to the shear stress here, then consequently for this surface it will be pointing downward. Similarly, this surface is also a dominating surface because it is better aligned to the vertically upward shear stress on the left hand side. Therefore, on this surface there is also an upward shear stress, and consequently you can draw the rest of the shear stresses like this. So the 2 arrows are pointing to each other. However, for an element in the positive torque, it is tensile in this direction while it is compressive in this direction. Here is some summary. For shear stresses, first determine the dominating surfaces as we mentioned, and then draw the shear stress on that dominating surface following the direction of the vertical shear stress. Then you can draw the rest of them easily. To draw the direct stress, for positive torque, it is tensile in this direction, while it is compressive in this direction. For example, for a stress element in positive torque, the positive torque means that there are 2 shear stresses like this on the left and the right hand side of the stress element. So for those 2 dominating surfaces, we can immediately draw the shear stress on it, and also we can draw the rest of the shear stresses. Besides, since it is in the positive torque, it is tensile in this direction. That means the direct stress is sketched like this. Since for each stress element there is a pair of tensile stress as well as a pair of compressive stress, then we can conclude that there is also a pair of compressive stress acting on it. So this is just how you determine the direction of the stresses on this piece of material. In fact, in order to determine the magnitude acting on it, you have to use our 2 equations introduced before. So those things are just for you to determine the direction, while those 2 equations are used for you to determine the magnitude. Besides, on the textbook there is also an important conclusion. The relationship between the maximum shear and the normal strain in the pivot torsion is given by the maximum axial strain equals to 1/2 of the shear strain. Let's quickly go through a past homework problem. A solid circular bar of diameter d equals to 50 mm is twisted in a testing machine until the applied torque reaches the value T equals to 500 Nm. And this value of torque, a strain gauge oriented at 45 degrees to the axis of the bar, gives the reading of epsilon equals to 339 times 10 to the power minus 6. You are asked to determine the shear modulus of the material, the Young's modulus of the material by considering the stress element, as well as sketch the stress elements counterclockwise oriented at different angles. To determine the shear modulus of the material, conventionally we would like to consider some formula like tau equals to g gamma, right? Because we only know on this strain gauge there is an epsilon, but we don't know about gamma. However, there are a lot of information missing, but one thing we can utilize is the formula I just introduced to you. Still remember that for a 45-degree inclined element, there is no shear stress acting on it. Instead, there is axial stresses acting on this element. Still remember that for the positive torque, it is tensile in this direction, while it is compressive in this direction. Under this case, this stress element is under the maximum axial strain. Therefore, we can find the maximum shear strain inside this bar by using this strain gauge inclined at 45 degrees. Since the maximum axial strain measured by this 45-degree oriented strain gauge is given by 339 times 10 to the power minus 6, then the maximum shear strain is just twice of it, which is 678 times 10 to the power minus 6. Consider in the very first step, when we derive the torsional formula, we write the shear stress inside the bar in this form, that is the ratio of the shear stress to that of the maximum. Then the maximum shear stress can be written as G, the shear modulus, times the maximum shear strain, gamma max. And then you absorb this term into the row behind. Consequently, by integrating both sides, you can find the torque acting on this bar equals to the shear modulus times the maximum shear strain times the polar moment of inertia divided by its radius, where polar moment of inertia can be found easily by using this expression. Consequently, the shear modulus of this material, by substituting the numbers into it, is given by 30.04 gigapascals. Now, by using our information in part A, we can find the maximum shear stress inside this material, which is 20.37 million pascals. Consider this 45-degree inclined stress element. For the 45-degree inclined element, the maximum tensile stress acting on this is just the maximum shear stress, but you know it is just E times epsilon, E times the axial strain. By substituting the values into it, you can find the Young's modulus of the material is 60.09 gigapascals. You may observe that, wow, why? This number is just twice of the shear modulus. Well, it is just considering this inclined stress element, but it is left to you to think of why. Next, we need to sketch the stress element counterclockwise oriented at 22.5 degrees, 30 degrees, 45 degrees, and 60 degrees. Firstly, let's consider a 22.5 degrees counterclockwisely oriented element, which is like this. For the positive torque, the shear stress is on the left hand side and the right hand side is like this. Therefore, we can say that the stresses on the two dominating surfaces is like this, and we can sketch the rest of them. Besides, since it is a positive torque, the direction of tensile axial stress is like this. Therefore, we can determine the direction of those two forces, the axial tensile stress on this stress element. Finally, we can draw the rest of them. As what we discussed in the previous special case session, for the 22.5 degree oriented element, the magnitude of all forces acting on this stress element is just the maximum shear stress divided by square root 2, which is 14.41 million pascals. So all stresses have the magnitude of 14.41 million pascals in this figure. For the 30-degree counterclockwise oriented element, first we determine the directions of the stresses on this stress element. For this element, it is just 30-degree oriented. The positive torque will generate the shear stress like this. Then we can draw the shear stress on the dominating surfaces, and we finish the rest of them. For positive torque, still the axial load is tensile in this direction. It is compressive in other directions. It's done. So we have determined the direction of all shear and direct stresses on this stress element. The magnitude of the shear stress acting on it is 10.19 million pascals, while the magnitude of all axial stresses is given by 17.64 million pascals by using the equations we derived before. 45 degrees is a rather special case. In this case, there is no shear stress acting on it. There is only the axial stress, and as discussed before, for the positive torque, it is tensile in this direction, while it is compressive in this direction. All the stresses inside this figure has a magnitude of 20.37 million pascal. Talking about the 60-degree oriented stress element, originally the element looks like this, and when it is 60-degree oriented, it will be like this. On this stress element, for the positive torque, there were two shear stresses like this. Consequently, we can draw the shear stresses on the dominating surfaces, and we can finish the rest of the shear stresses. For the axial stress, similarly, for the positive torque, it will be positive in this direction and the negative in this direction. The magnitude of all shear stresses is given by 10.19 MPa, while the magnitude of all axial stresses is given by 17.64 MPa. Let's move to our final topic in this chapter, which is the shear stresses in the thin wall sections. Previously, we considered the change of shear stress along the radius or the distance from the centroid of the cross-section. We draw a conclusion that tau varies directly to the distance from the centroid of the circular cross-section. However, in the thin walled sections, we assume the tau is a constant. To do this, we will introduce the Bugert-Bethel theory. Excuse my pronunciation. Before we derive our formula, let's discuss about our assumptions. First, the cross-section should be a closed cross-section. Besides, we assume the thickness of the cross-section is very thin, such that there is no change of shear stress across the thickness. Now, we draw a differential piece of material from this closed cross-section and take the force equilibrium. Then, by considering those two forces, we know that tau1 T1 dz equals to tau2 T2 dz. By cancelling the dz out, then we have tau1 T1 equals to tau2 T2 equals to Q. It is an important quantity in solid mechanics called the shear flow. The theory is derived by considering the differential torque dt equals to QR ds. Consider a piece of material under the shear flow Q with the length ds. Since for the shear flow, it has already taken the thickness of the material into the consideration, then Q ds is just a force, a differential force acting on this differential element. Therefore, we can write the differential torque equals to the differential force times the arm, the length of the arm, r. As what we derived, Q is a constant, it is uniform. Besides, we consider the area of this very small triangle swiped by r. For this very tiny piece of triangle, this is ds, and its height is r. Then the area of this differential region is given by dA equals to r ds divided by 2, according to the triangle area formula. Therefore, since Q is a constant, it can be taken out from the integral. Therefore, we can write T equals to Q times the circular integral of r ds over the entire length of S. Since dA equals to r ds divided by 2, we can find the area enclosed by the center line of the thin walled structure. The area is given by 1/2 of the circular integral of r ds over S. Consequently, this item will then become 2a. Therefore, T equals to Q times 2a implies that Q equals to T divided by 2a. Since Q is a constant, which is the shear stress times the thickness, we conclude that the shear stress in the thin walled section is given by tau equals to T divided by 2AT. Here are some examples of the calculation of shear stress inside this thin walled section. First, for the circle, area equals to pi r squared, and since it has a uniform thickness, then T is just T. For this rectangular section, A equals to BH. So this is A, this is A. However, the thickness in this thin walled section is not uniform. The thickness here is T1, while the thickness here is T2. T2 is greater than T1. However, we can still calculate the shear stress inside this thin walled cross section. You replace T by T1 and T2 respectively to find the shear stress inside each member. Let's do some quick summary about this tutorial. First, we discussed about the derivation of the elastic torsion formula. The shear strain gamma is given by rho phi divided by L, while the maximum shear strain is given by r phi divided by L. Besides, we also defined a quantity called the rate of change of torsional displacement. Besides, we derived the torque in a circular cross-sectional tube in terms of the maximum shear stress. Besides, we also extend our understanding to the elastic torsion formula to multiple shafts and continuously varying shafts. We also did some examples on it. We also dealt with a statically indeterminate problem of pure torsion. Besides, We also learned about the stresses on inclined planes, as well as the method of drawing stress elements, especially how can you determine the direction of the stresses on an element. Finally, we discussed about a theory which helps us to derive the shear stress in the thin wall structure. Tau equals to T divided by 2AT. In this tutorial, there were 4 example problems, and I have already discussed them in detail. If you wish to test yourself on the understanding on this chapter, you are recommended to do these problems. For example 3.1 to example 3.4, the total marks assigned in this tutorial is 120 marks plus 10 extra marks. You can use the following table to estimate your final grade based on your understanding to the material in this tutorial. Finally, thanks for watching. If you have any comments and suggestions, please feel free to leave your comment under the video. Besides, you can also send me an email to talk about your suggestions for us. Finally, thanks for watching and see you in the next tutorial.